Siamo a Villaratti e abbiamo il piacere di avere in diretta Federico Re e Stefano Bondani, e quindi chiederei a Federico di iniziare la sua presentazione, che saranno 2 presentazioni, una successiva all'altra, di 25 minuti ciascuno, se per voi va bene.
Io mi ero preparato 45. Anche 45. Però...
vabbè, allora proviamo di ridurre a... Sì, va bene, a 45 minuti ciascuno. Sì, va bene. Procediamo, cominciamo, Federico.
Certo.
Tu vieni dall'Università di Insubria?
Ho fatto il PhD all'Insubria, sì.
Bene.
Adesso lavoro a Milano di Cocca.
E collabori chiaramente con Federico Hart.
Con Francesco Harzi.
Francesco Hart.
Il mio coautore. Sì.
Il coautore. Bene. Se per voi va bene, iniziamo.
Ok. No, attivo. Now I share the screen. Ok.
Ok.
Okay.
Yeah.
Do you see it? Then I can start. Good morning, everyone. Today I will talk about dark matter. So let me start with the most important phenomena of dark matter. First of all, the rotation curves of galaxies, which became flat in the region of the halo, but this does not match with any visible matter. So we need some dark matter to explain it usual. But also the measurement of the mass of galaxies with gravitational lensing, or the bullet cluster is a very interesting phenomena, or even the CMB anisotropies, and so on. So we have a lot of dark matter phenomena. In this lecture, I will talk mostly about the galaxy rotation curves. However, looking of all these phenomena, we can start with a simple observation. These are all gravitational phenomena. So someone could wonder if we can explain, at least for some part, the dark matter just as a fake dark matter due to gravitational phenomena, so not a real presence of invisible matter. This is the same idea of the MOND, the modified Newtonian dynamics. In the MOND theory, the very law of gravity is modified in order to explain dark matter. This is not what I will do in this lecture. In this lecture, I will just consider the general relativity. In fact, the general relativity is yet a modification of the Newtonian gravity. So we can start wondering if the correction terms due to general relativity can provide some relevant correction on the dark matter. Obviously, there are good reasons if this was not done a lot in literature. First of all, because post-Newtonian correction due to general relativity are usually negligible for a galaxy, since in a galaxy the speeds are sub-relativistic and the gravitational potentials are weak. So in general, we have a low energy limit in galaxy, and the post-Newtonian terms are negligible. Second of all the GR metrics can be put locally in a Newtonian form, this form. And in this form, all the GR correction are post-Newtonian. So again, they are negligible.
Thank you.
However, we try to consider GR. Why we try? First of all, because a galaxy is an extended source. So we need a global metric. and the metric is not necessarily globally Newtonian. In general, we can have some off-diagonal terms in the metric. And due to these terms, the low energy limit is not always the Newtonian limit. In general, we can have firstly the Newtonian law, then the post-Newtonian correction, but also some additional correction as gravitomagnetism and so on. And all these dragging terms, all these off-diagonal terms, can return some non-negligible correction, even at the first order. This is what we want to do today. Let me recall briefly what is gravitomagnetism. The gravitomagnetism arises when the metric has this form with this off-diagonal term, and it is a formal analogy with are you seeing my slides? Do you see everything?
No, we see the first slide only.
Sono fermi alla prima.
Esatto, sono fermi alla prima.
Ah sì?
Anch'io vedo fermo alla prima.
I see the first transparency.
Provo a ricondividere lo schermo, ok?
Adesso è giusto.
Ok?
Ah, non era condiviso.
Sì. Vai, prova a fare un pochino. E comincia da capo.
Sì.
Do you see now?
Yes. Sì, no, si ferma su quella introduction electromagnetism versus forse quando tu fai schermo pieno, fai condividi schermo pieno, cioè condividi tutto invece che soltanto pieno.
Proviamoci. Un attimo,
Ok, adesso però non è esatto, condividi tutto, non fai schermo in alto a sinistra, non fai schermo in alto a sinistra, così c'è solo quello che tu vedi e quello che tu vedi.
Ok.
Adesso per la riunione di Zoom. Scusi, sì. Ok, adesso vedo.
Now do you see it?
C'è un po' di ritardo.
And now?
Adesso io vedo questo.
Il prossimo. Fai il prossimo. Sì.
Does it work? Ok.
Ok, adesso sì. È in modalità, vediamo le tue prossime slide, però almeno se riesci a mettere solo la slide centrale, perché noi vediamo la precedente e la successiva anche.
Ah, ok.
La modalità di presentazione. Ok.
No.
Va meglio così che prima. Sì, arriva bene.
Non so come togliere una delle due, purtroppo.
Guarda, direi che così va bene.
Sì, sì.
Va bene così?
Sì, va bene.
Ok. Ok, I was saying that there are good reasons if we want to use GR, because in a galaxy we must consider a global metric which is not necessarily Newtonian. There are some dragging terms, and these terms can provide non-negligible correction to Newton at the first order. For example, due to the gravitomagnetism. The gravitomagnetism is a phenomena arising from a matrix with this form, and it is formally identical to the electromagnetism. The Einstein's equation takes the same form as the Maxwell's equations. Just if you are asking that the matrix is stationary, this is the only difference essentially. The metric must be stationary. But about gravitomagnetism, you will hear the lecture of Davide Astesiano, one of my co-authors, next week. So let me see the goals of our work. We want to try to re-weight the dark matter in the disk galaxies. So we want to take account of the relativistic terms, and we want to see if the new weighting of the dark matter changes in some ways. In general, we can expect that some part of what is believed to be dark matter can be just fake dark matter due to GR phenomena. But it could remain, of course, some part of a true dark matter. And it is important to estimate how much is this true dark matter and what features has. For example, we can imagine a lot of scenarios. It depends on what we find with this reweighting. Maybe we can find that the dark matter doesn't exist inside the disk galaxies, but it could exist, for example, in the biggest galaxies. In this case, we could conclude that the dark matter is some way hot, so it would be useful to detect it. Or another possibility is that reweighting the dark matter, we could find that it is quite less than it is usually believed. If it is just the 8% about of the total, the true dark matter, then it would be explainable with the massive compact objects, or so on. We cannot say for now what is the result of this reweighting. This was the introduction. Now let me see some literature about this line of research. First of all, this was the first publications about the GR in disk galaxies. Unfortunately, this was unphysical. The first physically reliable model was by Balazin and Grumil in this work. And he assumed a rigidly rotating dust in order to model the galaxy, so with the Langsos metric. And they found, using this ansatz, that the required matter, according to their model, was reduced with respect to the Newtonian model. And this is exactly an example of what I intend with reweighting the dark matter. Here, in the Balazin and Grumiller model, the dark matter does not vanish totally, but it is just reduced with some factor. The first empirical work about this research was by Maria Teresa Crosta. She considered the data from the Gaia DR2 catalog, and she found that for the Milky Way, the BG model matches exactly. So for the Milky Way, Maria Teresa Crosta does not need any presence of dark matter. And there are also some interesting papers about gravitomagnetism. And last but not least, here we have our papers about this work. Today, I will present two papers. The first one is a more theoretical paper where we generalized the BG model to the non-rigid rotation. And I anticipate the result. We found that our non-rigid model explains even more dark matter than the BG model, and yet the BG model explained more dark matter with respect to the Newtonian model. And especially, we found that the reduction of the required matter was in the halo region. This is especially interesting because the dark matter is usually believed to be concentrated in the region of the halo. And then we brought this second work, which is more empirical. We here proposed an empirical check of our theories. Let me start with the first paper, the theoretical paper, in order to show you the theoretical framework of our work. We started from some assumption. They are a simplifying assumption. So first of all, we considered a stationary and axis-symmetric galaxy. So with this form of the metric, with, of course, an off-diagonal term. Since we want an axis-symmetric galaxy, this means that we need a perfectly homogeneous galaxy without structures as bars or spirals and so on. Second assumption, we modeled the stars as particles of dust without pressure, so with this stress energy tensor. Third, we neglected the velocity dispersion. So in each point, the forward velocity is uniquely defined with a differential rotation omega and with a normalization factor h. The solution. The solution can be found in the literature of theoretical GR, since this kind of problem, the stationary and axis-symmetric metrics, were studied a lot. So we could just read the abstract solution in the textbook. These solutions are uniquely identified with the choice of two parameters. Two non-gauge parameters, pay attention, the eta parameters and the h parameter. H of eta is an arbitrarily free one variable function, while eta is fixed once one choice the form of this abstract f function. This can be expressed with a second order PDE on eta. So, summarizing, we have 2 degrees of freedom. The first one is the each function, which is a one variable function. And the second degrees of freedom is essentially the eta function on the galactic plane. Due to the second order PDE, all the shape of eta is fixed along the zeta coordinate. Once these parameters are chosen, all the Einstein equations are fixed. We have the equation of motion in this form. We have the formula for the differential rotation. We have the metric components. This is the last metric components, the space one, which is defined. And we have finally a formula for the density distribution. This is the key formula in order to estimate the amount of matter in the galaxy and the dark matter in the galaxy.
The parameter eta again.
The parameter eta is an abstract parameter for now, but we can interpret what is eta in a physical sense if we choose an observer, a frame, if we choose a frame inside our space-time. The most natural frame to use is the ZAMO, the frame without angular momentum. This is the tetrad, and in some sense, we can say that the ZAMO frames rotates with the metric. So the ZAMO has a non-zero angular speed in general, which is this key.
It's like a rest frame.
Yeah. According to ZAMO, measured by ZAMO, the dust has a velocity v, which is exactly eta on r. So we can substitute everywhere that eta is equal to r times v, simply put. Pay attention, this v is not the speed we read from the rotation curves. This v is just the speed measured by ZAMO. Because when we measure a rotation curve, what we do is to see the redshift of the galaxy. And this redshift is not necessarily the same experienced by Zano, because we are not inside the galaxy. We are far away. We are looking it from far away, and we are just measuring the redshift. So we will return to this point. For now, take account that this V is not W. We call W the speed in the rotation curves. We call V the speed measured by Zano. Okay. Using this V measured by Zano, we can substitute it inside all the formulas as inside the metric components or inside key and so on. So now we have our abstract solution. This abstract solution should be asymptotically Minkowskian, of course, because the galaxy is a concentrated source. And in order to get it is asymptotically Minkowskian, there are two ways. First of all, if our metric applies to all the space-time, we must ask that the limits matches with Minkowski at infinity. But it could happen in some cases that our metric loses validity at some big R. Maybe because the density becomes negative. In this case, we would paste our solution to an external solution that must be a home solution, of course. And this must be, again, asymptotically Minkowskian. This is the theoretical framework. We can start to compare it with the most common models. First of all, the Newtonian model. We can find again the Newtonian model as a subcase of our general metric, if we ask that there is no dragging term, and if we ask that we have just low energies. In the Newtonian model, we have this form for the metric. And we remember that the Newtonian model is completely defined by just 1 degree of freedom. Newton has 1 degree of freedom. So, for example, if we know in a Newtonian model what is the distribution of matter, it fixes everything. It fixes the potential, it fixes the rotation curves, and so on. And this is an important difference with respect to our model, because we have 2 degrees of freedom. We have first the speed in the galactic plane, and second, we have the H parameter, which is an intrinsically general relativistic parameter. So, for example, when we evaluate the distribution of matter, we have this Newtonian formula, which depends only on the speed, while our formula depends on both the speed and the L parameter. L is defined as the logarithmic derivative of H, okay? Again, we have an interesting difference with respect to the Newtonian model, because remember, we asked that our dust must be pressureless and must have no velocity dispersion. These are quite unphysical requests, but we can solve these requirements in a theoretical way. Theoretically, in a Newtonian galaxy, if there is no pressure and if there is no velocity dispersion, then the galaxy must collapse on an infinitely thin disk, or it must be an infinite cylinder in the zeta direction. This is the Newtonian case. But this is not the general relativistic case. In general relativity, these two requirements lead to a more complicated equation. This is the quite complicated equation we found. We called it the velocity field equation, because this is essentially a requirement on the velocity distribution. This is more complicated, but it allows also some anti-intuitive solution. For example, is in both cases, in both the Newtonian and in the general relativistic case, we are describing a non-physical galaxy. Okay, so if we consider the dependence on zeta of our model, this is not physical. This is described by the VFE, but it is not physical because in a physical galaxy we have pressure and we have velocity dispersion. Our model, pay attention, is reliable only on the galactic plane. For little values of zeta, it is reliable. For bigger values, it is not reliable. But we will consider now just quantities on the galactic plane. So on the galactic plane, our model is reliable. Okay, we compared it with Newton. Now we can compare it briefly with the gravitomagnetism. We have the gravitomagnetism in this case. So again, with low speeds, but with a non-zero dragging term. This is the metric. And in this case, essentially, the gravitomagnetic potential matches with the off-diagonal term of our metric. Last but not least, we can compare our model with the BG model. Remember that the model by Balasin and Grumiller was a rigid model, so it is a subclass of our model. We have, in general, non-rigid rotation. So in general, we have omega different from 0. We find again BG model if we set
BG model now.
BG model was the model in the publication of Balasin and Grumiller. It is essentially our model, but in the subcase of rigid rotation, while we are considering in general a galaxy which is not in general rigidly rotating. So the BG model is a subclass of our model with rigid rotation, so with omega equals 0. So with the metric, which is a Langsos metric. For the BG, our velocity field equation boils down to this simple equation. And we can see that if we compare the formulas for the density of matter, we see that in our case, with a non-zero L, we require less matter than in the BG case, just because the L term is a term that describes the non-rigid rotation, of course. If there is a non-rigid rotation, there is some subtraction from the required from the required density, and hence we can conclude that even if Balasin and Grumiller required less matter than the Newtonian model, we now require even less matter than BG. Here an example. In general, for a galaxy, we don't know the shape of the parameter L. It is in general a function L of eta, but we can calculate it in some simple case. For example, for constant L. We choose a constant L with this form. According its unit of measure, with this form, it is comparable with the scale of greatness of the galaxy. Okay, so in this case, this is the velocity field equation in the region of the halo, and it allows the constant solution for V. So it allows a flat rotation curve in the region of the halo, which is exactly what we observe, and which is the origin of the problem of the dark matter in this case. Moreover, if we substitute our solution inside the formula for the density, we see that the reduction of matter with respect to BG is concentrated exactly in the halo. When R approaches to the radius of the galaxy, the matter is very reduced.
Asymptotically, on the border.
It is not asymptotical. It is not asymptotical. Now I show some graphics in order to see it better. Okay. we choose, if we choose the same ansatz of BG for V, we already know that there is a reduction in the BG model with respect to the Newtonian model, but we have an additional reduction in our model. This is the ratio. This is the ratio between the Balazs-Lenggru-Miller mass and our mass. Here we see that the ratio is near to 1 in the internal part of the galaxy, and it reaches 0 in the halo. It becomes also negative after the radius of the galaxy. So this is exactly one of these cases when we will need some vacuum external solution after the density reaches the 0. However, recall it, we have a reduction of the dark matter exactly in correspondence of the halo. These were the results in our first paper. So if you want, we can take a break. This was the first half of my presentation. Do you want to take some minutes of break?
It's okay. Maybe there are questions, comments.
I show you online.
Carlos.
Yes, I will do a question. Yes, so I activate now. Can you hear me? So yeah, my question is, have you test or compare this general relativity solution with, for example, the various mass models typical of a disk galaxy, for example, bulge plastic disk of typically used to model rotation curve in these galaxies, which are the difference. And because of you have test the behaviors, right? If you can get the flat region and the correction respecting Newtonian, but I think for you it would be interesting to compare with actual mass models of galaxies. For example, the Newtonian thick plastic is used in the Milky Way or in other galaxies in order to see.
We are now trying to compare it with this distribution. We didn't. This was not done for now, but we are trying to do it.
Okay.
Good.
Hello, can I have a question?
Then I think we can continue.
We continue. Okay.
Can I have a
So
question?
if we continue, I start with the second publication, okay, which was the more empirical publication, where we proposed an empirical check for our hypothesis. Well, how can we find an empirical check? What we see when we observe a far galaxy is essentially the visible matter and the redshift. The redshift is what we measure when we draw the rotation curves, right? So what we need to do, first of all, is to estimate how much is it, the redshift, in the GR case, because we know that with a Newtonian metric, the redshift is just a kinematical redshift described by special relativity. But in general relativity, with non-negligible correction, the redshift could depend on both the kinematical redshift and on some gravitational redshift. So in general relativity, the formula would be most complicated, and we have to take account this complication in order to interpret in the right way the rotation curves, because these could be not due just to the speed. if this is a curve of a redshift and not simply a curve of a speed, this can be due on both the real speed of the galaxy and on the distortion of the geometry, right? So we have to take account to both of this. We calculated the most general formula for the redshift. We considered a galaxy. We considered that we are observing a galaxy with our metric. We are observing it from the infinity. So we are in the Minkowskian region. The galaxy can be tilted of some angle with respect to our line of view. And we can assume that all the gravitational fields are weak, so that the relativistic aberration can be neglected, and we can approximate all the quantities at the first order. Okay, we perform all the calculation of the redshift. I can skip this part, I think. I can show it after if you want. I skip just to the last formula. This is the formula of the redshift in general. It is quite complicated. It depends from the three coordinates inside the galaxy, the three cylindrical coordinates, and it depends in general on the angle of which the galaxy is tilted. So we have this complicated formula. It depends on the parameter or the parameters of the metric, the H parameter, the omega parameter, the V, which is here inside the Lorentz factor, and it depends in general also on the angle theta. Theta is the angle between our line of view and the speed of the star, which are emitting the photon. Okay. So this is the general formula. We already see that it is different from the special relativistic formula. We can evaluate it in some specific case. First of all, we can evaluate it for the BG model, so in the rigid rotation case. In the rigid rotation case, omega is 0, hence the redshift vanishes. This is a quite strange result, but because it is quite strange because here the formulas are saying that if we look at a galaxy which is rotating, but it is rotating rigidly, then looking just at the redshift of its stars, we do not see any redshift. So we do not see that it is rotating. Why? How can it possible? Here I show you some sketches just to see intuitively what is happening. Okay, we have a galaxy. We have a galaxy which generates a dragging metric, right? So in a dragging metric, the geometry is distorted near the galaxy. We can say that the space is compressed near the galaxy, okay? While we are observing it from the infinity, where we are in a Minkowskian metric. So here our space is not compressed. Hence, if a wave is emitted from the galaxy, then its wavelength will relaxate, traveling along the path, just because it follows the relaxing space. Do you follow me? Now, if the wave emitted is yet redshifted, because the source has some speed, so there is some kinematical redshift, this kinematical redshift will be cancelled with respect to the gravitational blue shift. In this case, in the rigid case, the gravitational blue shift and the kinematical redshift are exactly cancelled. So this is the first strange result from our redshift formula. And we can conclude that all the galaxies are non-rigidly rotating, because if we look to any galaxy, we see a non-zero rotation curve, right? Hence, the rotation of the galaxy cannot be rigid due to the calculation of the redshift. So this enforces the use of our model instead of the BG model, since the BG model will provide just a zero redshift, while we see physically a redshift. So we need the non-rigid model in order to describe a galaxy with general relativity. Second of all, we see other particular cases. We can consider a galaxy which is face on with respect to our line of view, and we can consider also the other particular case, the edge-on galaxy with respect to our line of view. For a face-on galaxy, the redshift is just a transversal redshift, and it is simply in this form. For an edge-on galaxy, the redshift is mostly a longitudinal redshift, and it has a quite more complicated form. This is the formula, and it can be put in this form so that in the Newtonian limit, it boils down just to the special relativity formula. We can define again the special relativity in the Newtonian limit. Okay. If we compare these two formulas, the formulas for the transversal redshift and the formula for the longitudinal redshift, we see that the transversal redshift measures exactly the h parameter, while the longitudinal redshift depends only on the omega parameter. So our idea is this one. We can measure simultaneously both the redshift, the transversal one, and the longitudinal one. And in this way, we would be able to fix all the parameters of our model. And this would provide an empirical check of our model as well. Practically, if we look to a far galaxy, okay? This galaxy is tilted with respect to our line of view. So what we see in our telescope is an ellipse, right? Okay, we can measure the redshift along the major axis of the ellipse and along the minor axis of the ellipse. On the major axis, we will have the longitudinal redshift, because along the major axis, the stars are moving longitudinally with respect to our line of view. While on the minor axis, with the same distance with respect to the center, so for the same r coordinate, on the minor axis, we have just a transversal redshift. If we can do this thing, we will have simultaneously both redshifts, and we will be able to compare them with the Newtonian prevision. Remember that in the Newtonian model, there is only 1 degree of freedom, so the two redshifts must be linked with a rigid proportion, okay? In the Newtonian case, if the Newtonian proportion results to be broken, then we can conclude that the Newtonian model is not reliable and some relativistic correction are needed. Let we see. In the Newtonian case, we have these formulas on the left. And so in the Newtonian case, we need to find this relation. The Newtonian prevision is that twice the twice of the transversal redshift must be the square of the longitudinal redshift. If we perform the measurement and we find this, then the Newtonian model is confirmed. If we perform the measure and we don't find this, if this equation is broken, then we need the GR in order to explain the galactic phenomenon. Moreover, if we have the measure of both redshift, we can fix all the parameters of the GR model, and we can substitute them inside the formula of for the mass density, and we can finally estimate the quantity of true dark matter inside the galaxy. It could be 0, it could be the same of what is usually believed. We can, of course, we could even find that the true dark matter is really the 80–85%, but we believe that we should at least try to do the check, right? Okay, this empirical measure needs some precautions. There are a lot of practical complications, of course, if we want to do this kind of measure. First of all, considered a still galaxy, a still far galaxy, but it is not the true case. A physical galaxy is moving with respect its cluster, and it will have also a redshift due to the Hubble expansion, of course. Moreover, another complication is that we are looking the other galaxy from the inside of our galaxy. The Milky Way is another spiral galaxy. So the Milky Way, we have again a metric with a dragging term. And this dragging term of the Milky Way will shift systematically shift the measure of the redshift of all the other galaxies. So these three complications will provide a systematical shift for all the redshift of the other galaxy we are observing. So these three contributions can be just subtracted considering the redshift of the center. The center should not have an itself velocity with respect to the galaxy. So all the redshift in the center will be due to these three shifts. And so for all the other points of the galaxy, we can just subtract the redshift of the center. And what we find is the internal redshift, what we are interested about. There are other complications. Because in a real galaxy, there are some macro movements of its structure, okay? For example, the galactic plane is warped, or the bars and the spirals and in general the structure of the galaxy can buckle in some way, and the center itself of the galaxy can wobble. And all these motions can be transmitted to the stars and can change the ideal velocity of the star. So we have to take account to these macro movements in order to perform the measurements. So is the measurement really feasible? Well, we can estimate the order of magnitude of what we want to measure. What we really want to measure is the transversal redshift. This is the real difficult quantity to measure because it is a second order quantity. So what is the order of magnitude of the transversal redshift? We can estimate that the transversal redshift will correspond to a speed of about hundreds of meters per second. Okay, we have some instruments that are able to measure such speeds. For ecosystem, for exoplanets, we have spectrographs that are able to measure tens of meters per second. So it seems to be feasible comparing our instruments. However, unfortunately, there are differences between an exoplanet and a galaxy. First of all, for a galaxy, we have larger signal-to-noise ratio.
Can you elaborate this of the ISO measurement? Repeat again this point.
Okay, I repeat. We have some spectrograph as for example the iso-espresso spectrograph,
Yes.
that is able to measure
For a star.
for a star, for an exosystem, is able to measure with the redshift
Yes.
velocities of even at the order of tenths of meter per second. What we want is to measure a speed which is hundreds of meter per second. So in theory, instruments like iso-espresso is able to measure what we want. But iso-espresso and these kinds of instruments are able to measure such a little speeds just for exosystems, and there are differences. There are practical differences to measure a speeds inside an exosystem or a speed inside a far galaxy, because in a galaxy there is a larger signal-to-noise ratio. And second of all, a galaxy has a less integrated flux. So we can, of course, try to measure what we want with iso-espresso, but we would require a very big observing time. We would need about 100 of hours just to measure the transversal redshift in one point. So in practice, it is not feasible today, but it will be feasible in the next years with a bit more sensible spectrographs, for example, Iris Andes and so on. So for now, our measure is not possible, but it will be possible in the next years. Of course, taking accounts of the macro movements, etc., etc. Okay, that were our two publications. Now I can conclude saying that all our publications are about the galactic rotation curves. But if we want to reweight really the amount of dark matter in all the universe, we need to reweight it also for all the other dark matter phenomena, of course. So we have to generalize our relativistic approach that we used for the galaxy rotation curves to all the other dark matter phenomena. What we have to do in general is to considering the non-Newtonian phenomena arising from GR even at low energies. So if we consider any dark matter phenomena, the idea is this one. Take the dark matter phenomena, model it with GR, and then compare your GR model with the usual Newtonian model. Since in GR there are additional degrees of freedom for gravity, and these degrees of freedom are dynamical freedoms with their energies and momentum and so on, and they do not vanish at for low energies. Then whenever these additional degrees of freedom are involved in the phenomena, we can expect non-negligible corrections for dark matter. This is the general idea. We have to apply to all the particular cases. There are a lot of work to do, but we believe that it could be very useful in order to understand what the dark matter really is. For example, if you want to estimate the dark matter with the virial theorem, we need a generalization of the virial theorem. This will be an argument of the lecture of Davide Assesiano next week. Or maybe if you want to estimate the matter with the gravitational lensing, we need to consider the dragging terms in the metric that are doing the gravitational lensing. Or moreover, I already some works about the cosmological estimations, the cosmological estimation of dark energy and dark matter. Again, here we need to consider the most general relativistic model with homogeneities, retarded potentials, and so on. In conclusion, what we did in our works, we generalized the rigid model by Balasin and Grumiller. We showed that in the non-rigid model there is a reduction of mass, of the required mass, and we showed also that this reduction is concentrated in the dark matter halo. Moreover, we found a general formula for the redshift. We showed that for the rigid rotation the redshift is 0. And we proposed an empirical check measuring both the redshift in order to check if the GR is really necessary or if the Newtonian model is sufficient to describe a galaxy. There are some limits for our work. We considered idealized galaxies with zero pressure and velocity dispersion, as I said. And there are some differences for the measure we want to do. And finally, we can say also that all our works is about disk galaxies. But what about elliptic galaxies, for example? So there are a lot of future work to do. First of all, we will generalize our metric, for example, with a non-zero pressure, since a non-zero pressure can mimic a velocity dispersion. Or, on the other hand, we can practically, numerically consider a velocity dispersion with some numerical simulation. We are doing it. We have to calculate, of course, all the macro movements for the galaxy, and we want to really perform the measure, the empirical check of for our theory. Moreover, we want to do other theoretical works. For example, we want to generalize in GR the virial theorem and apply it to galaxy cluster, to elliptic galaxies, and so on. We want to calculate the general relativistic version with dragging of the gravitational lensing. We want to study the shape of the L parameter for different kinds of galaxies. For example, in the next year, we discovered some fluffy galaxies, you know, which are disk galaxies with a very, very low density of mass, and they result to have no dark matter. So they are a very interesting case to study, and we want to see if our model can match with these fluffy galaxies with a suitable L parameter. And last but not least, we want also to consider the time dependence of our model, because we consider it for now just stationary models. And this will be our future works. Thank you for your attention.
Thank you very much. Very interesting. Carlos, you have any comment?
Yes. Okay, so yes, I would like, probably related with your future prospects. I was wondering, because your main prediction of GR effects, you have shown that it may be due to the non-diagonal terms on the energy stress tensor due to the dragging effects respect to Newton.
The non-diagonal terms of the metric.
Of the metric.
None of the stress tensor.
Sorry, of the metric. And yes, but this is mainly because you apply to this data that you expect this this effect. But then, for example, in dwarf galaxies, which are galaxies dispersion velocity dominated, which is being shown that the proportion of dark matter is considerably, is sometimes achieving 90% of the content of dark matter. then what do you think would be the effect of GR, considering in that galaxies the non-diagonal term of the metric are negligible?
Yes.
How do you expect to I mean,
Well,
or maybe in that case you really for supermatter?
Well, we have to do calculation, of course. For now, I can say two things about elliptic galaxies. First of all, we can say that if the GR reduction is due to the average rotation, then of course in the elliptic galaxies the average rotation is less with respect to the spiral galaxy. So we can expect that could there not be a reduction of mass, and this is exactly one of our work hypotheses. One of our work hypotheses is the possibility that the dark matter could not exist inside this galaxy, but it could exist inside the elliptic galaxies.
Yes.
In this case, since the elliptic galaxies are quite bigger, this would mean that, that the particles of dark matter would be very hot, so only the gravitation of a big galaxy is able to catch them. The second thing I can do is that in elliptic galaxies, the velocity dispersion dominates, of course. So we will need different instruments to analyze at this galaxy, and this is exactly what we want to do with the virial theorem. We want to analyze the dynamic of an elliptic galaxies, not with the dragging axis symmetric metric, but we want to analyze this galaxy with the virial theorem in the general relativistic version. So we can also wonder if in the general relativistic version the virial theorem will take account also to the energy of the gravitational fields, for example, and in this case we could find a reduction of the dark matter also for elliptic galaxies. But these are just hypotheses for now. We have to make the calculation.
And one more problem is there are, for example, now, if you want to test even further the hypothesis in these galaxies, there are measurements of the weak lengthing now, which are quite precise in some galaxies, and probably interesting if you can make a check for the stress terms of the shear stress, due to lengthing. Besides your checks for redshift, because then you can also try to compare, because the light in your hypothesis of
dragging,
you should be able maybe to predict the changes in the shear stress.
Yes, we would like to do exactly this.
Yeah, there is also
exactly this. Yes.
Very interesting. Well, it is in a certain sense quite a fortune that this part of the discussion is taking place in Villavati. And the reason is that we have a tradition that people can send a wall in Villavati. And one of the last person who signed the wall upstairs was Morgan. And he was a student of Fermi. And Fermi was one of the last students of Fermi. And Fermi gave him as a topic of his thesis, Carlos.
activate your mind.
Oh, I see. Well, it is in a certain sense a good fortune that this meeting is taking place in Villavati, because we have a tradition to sign the wall. And one of the last students, people to sign the wall upstairs was Maury. And Maury was working on his thesis with Fermi. And the thesis was about the role of general relativity in galactic structure. It is incredible. Of course, Maury did not like the idea. At the time, this was very, 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 very premature. The data were not good enough. And Maury went on in particle physics and introduced the quark, and that was a great story. But by listening to you and listening to Carlos and all our work, it's clear that a new avenue of the role of general relativity in the galaxy is coming out. Because they are local structure, as you said, self-gravity, gravitomagnetism, which you have started to look into that. And in a certain sense, very likely, like Fermi used to work far, far ahead, although the data were not there, but the problematic was clearly there. Therefore, this has grown in one of the most important topics about dark matter, but also about galactic structure, and how to evaluate also the cosmological redshift and all these details. I congratulate you for the courage to start with Francesco Art, this beautiful work. And if there are no other comments, I would like to go to the second contribution, the one of Stefano BONDANI. Thank you again. I will show you next floor the signature of Gelman, and probably I will ask also you to sign this new adventure.
So may I just switch?
Okay, so next speaker is Stefano BONDANI. We will change a little bit topic, talking about primordial black holes as dark matter candidates. So you can start.
Okay. Please confirm me that you can hear from the connected computer.
Yes.
Okay, so thank you again for to the organizer for this beautiful opportunity to be talking about here. I will touch a few different subjects: dark matter, primordial black holes, and gravitational waves, and I will try to not make too much of a mess out of it. And the thing I would like to start with, of course, is this very familiar picture. And okay, that we all know about, of course, and I will follow from the previous talk of Federico very smoothly, where he ended talking about all the different challenges that have led us to talk about something that we have called dark matter. And of course, the first thing is rotation curves of spiral galaxies, and this plot was shown already yesterday. Federico has just been giving his beautiful talk about it in the last 45 minutes, and I'm sure Maria Teresa Crosta will talk about it again next week. And this is, of course, the most compelling argument, it was at least, to start talking about dark matter in the first place a couple of decades ago. Well, more than that, actually. And it seems that like now, general relativity is able to give an answer to it without recurring to any external matter component. So this is a good step forward in a promising direction. But there are many other problems that we are faced with that require an answer that we have called dark matter. For example, the formation of structures in cosmology requires that you form, of course, the potential wells with dark matter long before the baryons can fall into them, and so you can form the structures that you always see. And up until today, in order to simulate something that resembles what is the real observations, dark matter has been fairly central in something that is needed in order to reconstruct the observations with simulation. Or is it? Again, here I would like to propose to the attention a work very famous by Fermionic DM, where he showed a few years ago now that you can actually try and successfully solve the problem of structure formation with general relativity without recurring to the need of dark matter. So another step forward in a promising direction where general relativity could be hoped to solve this very pressing problem of needing dark matter. But again, we are not finished. There are reasons to believe that dark matter is to explain. Sorry. One peaks and valleys of the CMB spectrum are the way they are. For the reason is when photons get into and out of the potential wells at the last scattering surface, these potential wells cannot be built by anything else than dark matter. There was not enough structure for baryonic matter for the photons to actually behave the way that we do them behave in the CMB spectrum. So this still not has a definite answer. And of course, testing, as Federico told us about, is another problem where we are faced with a problem where today we have not a definite solution. So dark matter is still needed as a placeholder for this problem that still not has a solution. But I'm fairly confident that Federico and his team will be giving us an answer also to this, using the drugging with general relativity in the next years or decades, maybe. But let me just waste. Now, okay, so this is the picture that we have been taught in school, that we need a cold matter model. We need it cold because apparently warm is not as good to provide the correct formation of structures in the universe. We need it to be dark just because we don't see it, and we need it to be collisionless because of the dynamics that we need it for it to be. Okay, no worries in galaxies. But I would like to just spend a minute of time just saying that dark matter is just a name that we give to a problem. And this was a nice message that I received when you study with my professor of cosmology in Bologna. It doesn't mean that you must have a matter component in any way. It's just an unhappy choice of name. And the same way that you call dark energy a problem which you don't have the solution to. It doesn't mean that you actually have an energy component. The energy component in dark energy or the matter component in dark matter is just the easiest way to think about a solution for a problem that you have. So saying that you don't need dark matter is saying that you don't need a problem. That doesn't make any sense. You have a problem, but you can offer different perspectives to solve this problem. One of them is to postulate the existence of some exotic form of matter, or maybe you did not see any ordinary matter in the first place, or maybe you have to change your Newtonian theory, or maybe you have to adopt a general relativistic theory. It's up to you to decide what is the best approach. But the dark matter is just the name of the problem behind all of these tentative solutions. Okay, in the same way, if you want that the Big Bang is just a name that we give to something that we don't know about, but it doesn't mean it's not there. Okay, the problem is there, it's just a solution that is lacking. Okay, now that I've wasted a bit of your time, let's talk a bit about primordials. Why are we talking about primordials? I'll be clear in a second. But first of all, primordials were introduced in the 60s and 70s by Zatovich, Novikov, and then of course Hawking. And the thing is, as you can see from the dating of these papers, these primordial epochs were introduced long before dark matter was even a problem. So they were introduced all by themselves as a possibility that our universe offers, as something that can have been created in the primordial universe, and so that can exist. The fact that today we can hope to find some of a part of the solution to the dark matter problem with primordial black holes comes after this. So basically, in a few, primordial black holes are a possibility, and there are many possible formation channels that you can try and model. And the thing is, let's focus on the first row in this plot that I took from an online talk a few months ago. The thing is basically you are around the inflationary era of the universe, or just before the end of it, and there are strong perturbations that the metric and the curvature can have in the universe. You can have strong density perturbations allowing some black holes to form at actually any mass. So the mass range that you can see here goes from supermassive at the top end to dark matter, meaning any low mass that you might want. Okay, so the allowed possible mass range of primordial black holes is in theory unlimited. And in fact, what Hawking showed is that primordial black holes mass are only a function of the time of their formation. So if you plug in the number here, for example, when you are 1 second old in terms of universe lifetime, you will form a primordial black holes with a mass of 10 to the 5 solar masses. So already very big. If you want to form primordial black holes much smaller than this, you will have to form them long before 1 second has passed since what we call the Big Bang. So this is why they are called primordial black holes, because they are indeed formed at the primordial age. And of course, because these are black holes by all means, they will have, of course, a temperature, and this is the Hawking formula for the temperature. And because they have a temperature, this means that if they are emitting Hawking radiation, it means that they will have an expected lifetime. And for example, if you put a 1 solar mass primordial black hole inside here, you can see that its expected lifetime is very, very long. But because primordial black holes can have any mass, you can also plug in a very small number in place of this mass. So the age will start to go down and down and down. And indeed, what you find is that if the primordial black hole is small enough, it will actually have already evaporated since its birth today. So there is a threshold below which, in mass, the primordial black holes will have already evaporated, and up of which primordial black holes are still alive. And this threshold is about 10 to the 15 grams, which is about the size of a small asteroid. And this means that today we should be observing, if primordial black holes are a thing that exists, the evaporation of primordial black holes of roughly this mass. Okay, so arguments for trying to find dark matter in primordial black holes are compelling because they satisfy the requirements to be dark, to be cold, and to be mostly collisionless, because they are so dense that they can travel and roam almost freely. And so people have been trying for many years now to find dark matter in primordial black holes. So people have been saying, okay, maybe primordial black holes have a certain mass and they constitute a fraction of dark matter. And the work of Carr in this has been very precious because he has been putting out regularly his reviews. This is the latest from the 2021, so last year, where you can see all the constraints that comes from all different kind of observational constraints, of course, yes, to what is the maximum allowed fraction in dark matter that you can make out of primordial black holes. Okay, so on the left, you can see this red band is the Hawking radiation, and as you can see, there is 10 to 15 grams at the bottom, which is the threshold that I told you just about. And if you move right, you have a window where you can make 100% of the dark matter with primordial black holes between this range of masses. And then you move on and you find all kind of possible observational constraints like lensing, gravitational waves, accretion in light blue, the dynamics in green, the large-scale structure in pink, and distortion in the cosmic microwave background on the far up end of the masses. So as you can see, there are two windows, one very big masses labeled with capital D, one with very small masses labeled with capital A, where you could, in principle, try to make all of the dark matter in primordial black holes. But as you can clearly imagine easily, the D labeled window is talking about masses higher than 10 to the 14 solar masses. So this is way bigger than a big galaxy. So it makes little sense to think about some dark matter components that is a black hole much more massive than, let's say, the Milky Way. So not good reasons to look into dark matter into this window, and not good reason also to look into the very small window mass, which is labeled with capital A. The reasons are not so compelling as it was for the high mass window, but if you were to make any considerable amount of dark matter with primordial black holes this small, they would actually have to be everywhere, because they are so small, they would need to be almost everywhere, and you would have probably have noticed by now some of their effects. So the next best thing you can do is to look to the next best window, which is this small window labeled with capital C, which corresponds to about 1 solar mass. And so it looks like your best bet could be around this small window, where you could hope to make some 10% of the dark matter in primordial black holes, around 1 solar mass. And indeed, you can see the same thing that I just showed you in terms of the redshift to which the observational constraints are referred to. Okay, so I can go into this later on if you need it. But the thing is, by many of the possible formation channels that primordial black holes can follow, it appears that the 1 solar mass is the most favorite of all the possible masses that this multimodal distribution in mass is showing you. And it's telling you that you can actually be very confident that if primordial black holes actually exist, if they were formed in the primordial universe that we live in, they most likely will pertain to a 1 solar mass they will surely, most surely, appear to have a 1 solar mass. So if you have any model that you want to work with because you want to try and see if dark matter is made of primordial black holes and you want to try to observe them, it is a safe bet to start with 1 solar mass primordial black holes. So let's look at the galactic center. Let's look at Sagittarius star. Of course, now we have this very nice picture that I can shamelessly steal and use as the background for the outline of the second part of my talk. So we look at the galactic center because it's closed, so we can hope to make some good measurement out of it. And we are looking, as I just said, for a dark matter candidate, and many people have proposed them to be maybe primordial black holes. And if primordial black holes are indeed at least a fraction of the dark matter, they should behave like we expect dark matter to behave, like, for example, follow a density profile like the famous Navarro-Franken-White, which just tells you what is the density profile of any dark matter component inside your galaxy going to the center. And if you go close enough to the center, you will reach Sagittarius star, of course, the supermassive black hole at the galactic center. And maybe if these primordial black holes are close enough to Sagittarius star, if they have any angular momentum by conservation of angular momentum, they should start orbiting Sagittarius star. And maybe they are already doing so because the galaxy is very old, of course. And maybe if they are orbiting Sagittarius star close enough, we can hope to detect them with gravitational waves. So there are many maybes, as you can see in this slide, many ifs, many tentative ideas, but none of them are crazy enough to disregard them completely. They are actually fairly reasonable assumptions. And so people have been actually working on this for many years now. This is just a small extract of the many tens of papers that have come out that have been trying to look at exactly this very thing. because primordial black holes are a very compelling argument for dark matter. People have been saying if they are actually dark matter, they must be there. And if they are there, we should be able to see them with gravitational waves when they are orbiting something very big, for example, Sagittarius stuff. And so many of these works, you can go and read them, are basically have a point in common. And the point is, will ELISA, the large interferometer space antenna, which will be launched in the 2030s, be able to detect a primordial black hole of roughly 1 solar mass orbiting Sagittarius star? Will it have the sensitivity to do so? And the answer that all of these papers and many other that you can find in the literature will give you is yes, of course. ELISA is very well thought out. We have a very fine sensitivity, and so no problem to detect primordial black holes close enough that are spiraling into Sagittarius star, that are merging with it actually. But the question that you might be tempted to ask, and which we ask ourselves, is yes, ELISA is capable of doing so. It will be capable of doing so, but will it actually do so? Will it actually detect any primordial black holes? The question is, will they be actually there, close enough to Sagittarius star? And the thing is, we looked into any possible observational constraints that we have today, and the thing that we found is that you can constrain very precisely how much mass you can expect to find in a close enough region to Sagittarius star that you can put into primordial black holes. And so you have a very precise constraint into what you can expect to be able to see if anything is there in the first place. And so you try to sketch the first steps in your model. Let's assume circular orbits of these primordial black holes. Let's assume they all have the same mass, as I said, 1 solar mass, so a monochromatic mass function. And let's assume they did not accrete during their history, so they were formed at 1 solar mass, and they are today yet still at 1 solar mass. This is a bit of a debated point, but it looks like that if primordial black holes actually accreted during their history, we should be observing some signature in the X-ray background of the universe that we do not observe. And so it is reasonable to assume that no accretion took place during the history. So you have this picture at hand. You look inside, very close to the Sagittarius star region, and you look at the time that gravitational waves take to bring an object from the position where it is at to the merger, okay? And this formula is for a circular orbit. In the case you have any eccentricity in your orbit, you can just add this integral where A is the semi-major axis and E the eccentricity, and you compare that with the 2-baud relaxation timescale. So you open your Binny Tremaine or your Galactic Dynamics book, and you have just to plug in the velocity of your component and its density profile here. So let's assume, for example, the Navarro-Franken-White or any version of it that I just told you about. You compare all of this, of course, with the age of the universe, because if you're going upwards of it, you're not making any physical sense, and you can plot them. And as you can see, there is a competition between them. And if you are enough far away from Sagittarius star, you can see the distance from it in the x-axis. You will be dominated by 2-baud relaxation processes. But if you are close enough, gravitational waves will take over, and they will start to take less and less time for your system to respond. And so what basically happens is that whatever density profile that you have in this region, it will be 2-baud relaxed down to at least a few 10 to the minus 5 parsec from Sagittarius star. But then it would be greatly depleted by gravitational waves. It looks like it will have some sort of a sink. Your population will be decreased massively. You won't have many of these objects in case you had them in the first place, because gravitational waves are depleting them so fast. For example, let's take what people in the literature have been taking, a spiked version of the Navarro-Franken-White, which is given by this formula. And basically, you can see on the left plot that the density goes up and up and up, down until 10 to the minus 6 parsecs, which is basically the innermost stable circular orbit. And this would be an unperturbed profile where gravitational waves never took over. But if you let the time scale that I just showed you actually act, you will see that whatever is the density profile that you have on the external region, it will be greatly depleted by gravitational waves, and it will go down by orders of magnitude in density. Okay, and so you cannot expect to find many primordial black holes in the inner region because they are going down so fast by gravitational waves that they will not spend much time in that region. Okay. At the center, let's focus on the S cluster that was talked about yesterday in great detail, so I can go very quickly into this part. And let's zoom in into the very innermost region, the orbit of S2. This is a nice cartoon that I saw on an online talk that I screenshot. And it's just to tell you that we are looking basically at what is contained into this image. Okay, if there are any primordial black holes, we want them to be very close to Sagittarius star, because here the closest approach at S2 was about 14. I will go back to this 1400 gravitational radii. So just above a few milliparsec. Okay, you something very precise about the orbit of S2, which is its precession. Okay, and of course, precession you can calculate it very easily with this formula. And what you can do is take measurements of the orbit of S2 as best as you can do, and then measure its precession. And the Gravity came to help in the last years with this publication. But they actually looked at how precisely they could constrain the precession of S2, the orbit. And here is Mr. Genzel, I hope you can see it, which is presenting his work during a talk last year. And he's talking about this specific plot that turns out to be crucial for our work, that I can show you better in this slide. And it's basically telling you that inside the orbit of S2, inside the pericenter, okay, so 1400 gravitational radii, you can have at best 4,000 solar masses. Okay, so whatever it is that you have inside of there, it might be gas, of course. It's easier to think in this way, but you can have maybe faint stars that you cannot detect because they are too flammable. But maybe you can have dark matter. Maybe you can have primordial black holes inside of there, and there is a maximum amount of them that you can have there, and it is constrained by this limit. So whatever it is that you have there, it cannot exceed in its extended mass. That means the mass other than the 4 and a bit million solar masses that Sagittarius star is made of. You can make it to be primordial black holes. So for example, if I want my primordial black holes to be 1 solar mass, as I just told you in the beginning, I can have at best 4,000 of them inside the orbit of S2. Okay, and this is exactly what we did. We said, let's give it this, because many people have been very convinced about the possibility of having primordial black holes as a credible dark matter candidate. Okay, let's give it the best shot it can get. Let's assume that all of the mass that is permitted by these observations by gravity, so 4,000 solar masses, is actually all primordial black holes. And because 1 solar mass primordial black holes are the most favorite, let's go with it and see what happens. So you look at the geometry of your problem, and your detector, which will be an interferometer that we'll talk about in a minute, will have its orientation. The gravitational wave itself, in the moment that you model it as a plane wave, will have its orientation, and of course the source will be your primordial black holes orbiting Sagittarius star, so they will change their angle continually. And so these are fairly complicated formula for the pattern functions that define the sensitivity of your interferometer, okay, where alpha is the angle made by the arms of your interferometer. So in the case of LIGO and Virgo, you would have 90 degrees, but in the case, for example, of LISA, which will be a triangle, you would have 60 degrees. And all of these are the angles that describe your system, and the assumption that you can take when you need them to construct HFP, which is the time domain gravitational wave strain, is that your system is fairly persistent, fairly stationary enough that you can take safely an average of all these quantities. So you can end up with an average quantity for your gravitational wave strain. And once you do so, the only quantity that matters to you turns out to be the frequency of your gravitational waves, which is very much related to how far away your primordial black holes are orbiting Sagittarius system. Okay, and so when you have your frequency at hand and you say, well, my interferometer, let's say Lisa, will be flying for a certain number of years, I can expect to calculate how many cycles, how many revolutions the primordial black holes will make around Sagittarius star during the time that I will be observing them with gravitational waves. Okay, and with all these quantities at hand, you can calculate the signal to noise ratio, how much you can observe of these gravitational waves. Whereas you can see only the sensitivity Sn of f in this formula is missing. So the sensitivity is, of course, how capable is your interferometer to detect gravitational waves at a low enough strain. So let's focus our attention to two of the future space-based gravitational wave interferometers. One of them is Lisa, and of course, Lisa, of course, is also an artisanal lager beer, apparently, but also a gravitational wave detector, which comes with its own sensitivity curve. And let's not get into the details of this plot. It just suffices to say that, as you can see, the best sensitivity it reaches is between 10 to the minus 2 and 10 to the minus 3 hertz. Okay. Let's look at mu-RS. It is another gravitational wave interferometer that is now just been proposed for actually 2050. So we are looking fairly ahead of ourselves a bit. It's going to be, sorry, looking at the microhertz band. That's why the mu in the name, and it's going to follow the orbit of the planet Mars. That's why the RS in the name. So that's why it's called mu-RS. And it's going to bridge a gap in frequencies of gravitational waves that we will have between Lisa, which we cover down to 10 to the minus 3 or 4 hertz, and the PTA pulsar timing array and SKEA band, which will go at 10 to the minus 9 or something hertz. So it's just a proposal now, just a white paper. But it already, we can calculate its sensitivity once we know how it will be made. And as you can see, the sensitivity of Lisa is fairly up compared to the one of mu-RS, especially, it's not clear in this plot, but once you go down to 10 to the minus 4, 10 to the minus 5, 10 to the minus 6 hertz, the difference between the two interferometers is maximized. And this turns out to be crucial for our problem because, as I just showed you, primordial black holes, if they are there at the galactic center, statistically, you will not have many chances to detect them very close to Sagittarius stars, as I told you, because they will spend so little time there because they are going down fast, the gravitational waves. So they will spend most of their time at a distance, and this distance turns out to be exactly correspondent to this 10 to the minus 5, 10 to the minus 6 hertz. So this is already a spoiler alert for what I'm going to tell you in a moment, that mu-RS is the promising instrument if you are hoping to detect primordial black holes with gravitation waves. It's not Lisa. Just a funny picture that I find funny, at least. Lisa, as we know, is going to be the most massive objects ever built by man, and by far and large. But this record is going to be very short-lived. If you compare it with what mu-RS, which are these two blue and green triangles are, should mu-RS actually fly and be launched as a real mission one day. But let's stick to the theory now. So you calculate your signal-to-noise ratio for your single primordial black holes. Let's say you do 1,000 Monte Carlo simulation, you average out. Now you can, distinguish between sources that you can resolve, which have a high enough signal-to-noise ratio, and sources that do not enter this category, so they go into the background signal. Okay, and you apply these formulas here, and you end up with the results, which are, as you can see, not very promising for Lisa, because what this is telling you is that whatever your starting conditions, statistically, you have at best 1% chance, 10 to the minus 2 on the left-hand side plot, chance to detect any primordial black holes with a frequency of a few 10⁻⁵ hertz. Of course, in our system, which is very symmetric and very geometrical, a certain distance from Sagittarius star corresponds to a certain frequency, which corresponds to a certain signal-to-noise ratio. There is no overlap between these quantities. You can talk about one of them or the other seamlessly. But the thing, as you can see, is the chances of detection are fairly slow. And you can see the same thing on the right-hand side plot. That is just telling you that you got a 90% chance of never detecting anything, 0 observable sources during a 10-year observation lifetime. Okay, I didn't say this. Let's assume, for the sake of being optimistic, that LISA can observe for 10 years, which is, again, a bit of an optimistic guess, but still reasonable. During a 10 years observation time, only a 10% chance of observing one solar mass primordial black holes. So not promising. Let's see NUARES, the other interferometer that I talked to you about, what it can actually do, much better because of the difference in sensitivity at exactly the same frequency range which we are looking into. And this is not anymore a probability distribution, this is a number distribution. There is tens of objects that you can detect at all of these different signal-to-noise ratio or frequencies. And you can see the same thing on the right-hand side plot. It's telling you that on average, you can expect to detect a bit more than 100 of these primordial black holes. And this is well fit by a Gaussian distribution. So at least 100 of these primordial black holes should be resolved by ours. But now you can ask, maybe all of my primordial black holes went to the background signal and LISA might be able to detect it. Again, not promising. If you plot the characteristic strain against the sensitivity curve of LISA, you will see that all of them are below it. And this is translated in what you can see on the right-hand side plot, where the background of the, the signal of the background in gravitational waves is all contained below any threshold of signal-to-noise ratio that is reasonable, let's say 5 or 8 or 10. And you got a 1 in 1,000, okay, chance of having a signal-to-noise ratio. You can see in the very extreme right of this plot of having a signal-to-noise ratio above a threshold of say 5 or 8 or 10 or whatever. So basically it's telling you that you're not going to detect anything. The background of NUARES, again, is fairly promising. As you can see, because of the sensitivity curve goes down and this precise frequency range that we're looking into, also all of the non-resolved, most of the non-resolved sources fall into the band of NUARES, and this results also in a signal-to-noise ratio of the background fairly robust, well above 100. Okay, so good reason to promote and get funding for NUARES, if you ask. Now you can also sponsor us. I don't want a specific density profiles. Give me different masses, give me different profiles, because I'm hoping to find different answers. But as you can expect, not much changes. Don't get lost into this messy table right now. Just look into the paper if you want. The thing is, you can try and change the starting mass. We did from 10 to 10⁻² solar masses. You can try and change the density profile. We tried the spiked Navarro-Franken-White. We tried the isothermal sphere and the Bacallen-Wolf, which are the most standard density profiles that we generally use. But the results, although the numbers change a bit, show always the same trends. Okay, so the answers, if I am going or I am not going to detect primordial black holes with these instruments, basically do not change. I would like to just point out something that I find interesting into this table. Look at what happens at the resolved primordial black holes, column 5, let's say the top row, when going from high masses, so from 10 to 10⁻². As you can see, 0.05, and the more you decrease the mass, okay, the more the resolved primordial black holes increase. This is actually a probability. So you end up with a 42% probability. Why is that? Because the lower the mass of the primordial black holes, the higher the number that your constraint of 4,000 total solar masses is allowing you to have. So If you have one solar mass primordial black holes, which is the fourth law, you will have 4,000 of these objects. If you have 10 solar masses, you will have only 400. So there is an interplay, a competition, if you want, between the number of objects that statistically you can put into your system and the mass of these objects. And although the mass is clearly entering the equation for the gravitational wave strain, so the more massive, the higher the gravitational wave strain, the fact that higher masses imply a lower number appears to be dominant, okay? And as you can see, it is better to have very light primordial black holes, but a great number of them, because it appears that this aspect of in this competition is dominant, and it is more important to find statistically some of these primordial black holes close enough to Sagittarius A star to produce a signal. And you can have this when you have many of them, and you can have many of them if they are light enough. But now, turning your attention to mu-RS column 8, you can see a different pattern. You can see that low number, high mass, so first law, you have a certain number of resolved primordial black holes, and if you decrease the mass from 10 to 1, you can increase the expected number of primordial black holes that you observe. But if you go on, decrease again the mass, so increase the number, this stops. You go from 140 down to 53, down to 4, okay? What is going on here? Why is this behavior different from what happened with Lisa? And the answer is to be found into the sensitivity curve of mu-RS, which is this black line here. And as you can see, there is a plateau that is starting at around some 10 to the minus 6 hertz, okay? And it goes again, being flat up to 10 to the minus 4 hertz. So what is happening here is that it appears that by chance, this frequency corresponds to the intersection with the signal to noise ratio of one solar mass primordial black holes. So the more you start with lowering the mass of your objects, the better the sensitivity you are gaining from your instrument. But once you reach one solar mass primordial black holes, and this is all chance, there is no physical reason behind it, you do not get any more better in sensitivity of your instrument. You would actually have to go at higher and higher frequencies or lower and lower masses. So it happens that you get better and better just down to one solar masses, but then you can increase the number, decrease the mass, but you won't do any better because your sensitivity is not getting better. By construction, it will have this plateau here that is ruining your expectation of finding objects. The less massive they are, so the more numerous they are. So this was it. Let's look at the final aspect of our work. And of course, as I said, we have modeled our system to be very symmetric. So no eccentricity was assumed. The orbits of our primordial black holes were assumed to be very circular. But if you look at the stellar component around Sagittarius star, of course, you will see that most of the stars, in fact, all of them will have some degree of eccentricity. None of them will have zero eccentricity. And so the next thing that we are doing now, and is in preparation, we will publish in the following months, is to relax the no eccentricity assumption. And so we propose a system where you take into account some degree of eccentricity. And in fact, you can model this with a thermal distribution of eccentricity, where the probability of finding a certain eccentricity is proportional to the eccentricity itself. And this kind of a messy plot, you can see an unperturbed population in green dots of primordial black holes on the right of this gray curve that is the same that we had in the previous model, where just one point was the distinction between the two-body relaxation timescales and the gravitational wave inflow timescales. Now, because of eccentricity, at any semi-major axis, you can calculate the same thing at every eccentricity. And so this will draw you a curve, okay? So for any starting semi-major axis and eccentricity, you will have a time scale of crossing between the two regimes. And if you go down from the gray curve to the X crosses, you can read exactly what this time scale is. So if you take one of them, you will have say 10 to the 8th year is the time scale where gravitational waves take over and start to dominate your system. So you solve your differential coupled equation for the semi-major axis over time, the eccentricity over time, and you can draw this dark blue evolution lines, and you can populate randomly, extracting a random time between 0 and the gravitational wave time scale to populate again the inside region of this plot, by which you can end up with, for example, a plot like this, where the signal to noise ratio are the black dots, and the eccentricity distribution now is the orange dots. As you can see, most of them are in the high end of the spectrum because we assume a thermal distribution of eccentricity. And of course, because you have eccentricity, now you have all the harmonics in your orbits that will emit a different power. And you can calculate what is the harmonic where the maximum power is in gravitational wave is emitted. And you can plot these as well. And you can see, you can go up to 1,000. So the 1,000th harmonic will be the one emitting the maximum gravitational wave power for one of these primordial black holes. So an example of what you can expect to plot again your distribution in signal to noise ratio, and but this is just very preliminary, but very promising, because maybe you can expect many of the primordial black holes to enter the Lisa band thanks to the higher and higher harmonics they go into. But take this with a grain of salt. This is just preliminary work. I would like to just wrap up my talk. So in our system, in the search for a dark matter component into primordial black holes, you can actually do something, model something, and make some assumptions, but you can do much better than this. So one thing that you can do better, that I just show you in the last minutes, is to assume that you have eccentric orbits, which we are doing so. You can do some parameter estimation because, yes, LISA will maybe detect a one solar mass object orbiting Sagittarius star. Who is to tell me that is not a faint star or a neutron star that we do not see gamma rays out of because it's not pointing towards us, a brown dwarf, whatever it is. So some work has to be done in that context. And of course, you can extend the mass function. Maybe primordial black holes have not just one specific mass, but they have a distribution of masses. And if you believe this is true, you will calculate actually what is the signal coming from the galaxies that are in the local universe, because you can expect them to have similar condition to ours. Also, you can improve, of course, on the particle approximation and do some post-Newtonian calculation to actually be sure that you have done things as finely as you can. So as you can see, there is many things to do in the future, many more that have been done, of course. And so the road ahead is very long, but thank you for your attention for now.
Okay, thank you, Stefano, for the talk. We have some short time for questions. Mirabel has a question. Go ahead, Felix.
Yes, yes. As you know, in the galactic center region, we know there are many neutron stars of typically 1 to 3 solar masses.
Can I ask you to start again, please?
I couldn't hear. You ask, well, the question again. Well, we know that in the galactic center region, there is a very large population of neutron stars, and also probably black holes of stellar origin. I have several questions. So my question is, how will you distinguish a neutron star from a primordial black hole of 1 solar mass, 2 solar masses?
That is an excellent. That is an excellent question, and I thank you for it. And this is just, of course, the point 2 in this list. We still are not sure because we haven't completely looked into it at all, but it is a problem that we have very much in mind. And we expect to find a way, because the group is made of some people that are sure to be able to do this. I am sad to not be able to give you a more definite answer, but the question is excellent and is very much on point. It's something that we will look into for sure. It's something that we have taken into account for future work, but until now it was not. So sorry if this is not a very conclusive.
Very interesting.
Yes.
Very interesting also from my point of view. But what I wonder, if you have this ensemble of black hole up to 10 to the 4 and 10 to the 5 solar masses, large number of them. But if you consider the gravitational wave emitted, we know that the plunge will have the mass of the black hole times the ratio between the mass of the black hole and the mass of the cloud, therefore of the ensemble, therefore the gravitational wave emitted by each one falling and will be quite small.
I'm not sure.
If you consider the system, each black hole collapsing in the field of order 1, the field will be reduced by the ratio between the mass of the particle and the total mass. But we can discuss this.
Surely. The thing is, maybe this can help. Every primordial black hole constitutes with Sagittarius star a binary in itself. So it is treated as a binary in its own right, and will emit its own gravitational wave signal by itself. So you do this just many times, and that is it. Okay, there is no field interaction with the fact that all of these primordial black holes constitute a cloud of such. Okay, it is just, let's take a certain number of them, and each one of them will be a binary with Sagittarius star. Okay.
Well, this is a completely new idea. Okay.
Yeah, I have another question, Remy.
Used to say it's true, but very interesting. Thank you.
Thank you.
Well, can I ask a second question?
15 minutes, if it's okay with you, Felix.
Yes.
And in 15 minutes we join again.
Yes, and you speak, Felix, after the break, right? So
In 15 minutes.
Okay. Okay, fine.
Is that okay?
Yes. Yes, it's okay.
Hello. Felix, are you there? Can we start?
Yes, we can start.
Felix,
Okay.
well, can you hear me?
Yes, I can hear you. Do you see my slide?
Felix. Okay.
Yeah. Okay.
Felix.
Well, okay. I will.
Can we start?
Yes. Okay.
Per favore, verificate.
Is my screen being seen by you?
Felix.
Yes.
Can we start?
Okay. Well, I will talk about a subject that has interested me, and it is in the last 3 years, is the black holes that are seen in very early epochs of the universe. Let me show you this scheme of the evolution of the universe since the Big Bang until present day. And as you know, about 400,000 years after the Big Bang, it was produced the first atoms of hydrogen, and then about 200 million years after the Big Bang were formed the first galaxies with the first stars and black holes, and then there was an epoch that is called Epoch of Re-Ionization, when the atoms of hydrogen essentially were ionized, and this is why that lasted this epoch about 1 billion years. And this is, and the universe, the intergalactic medium became completely or almost completely ionized. And this is why we can see from the present epoch these early epochs of formation of galaxies. And as you can see here, the whole history of galaxy formation was a history of increasing structure of galaxies. Today, the most massive galaxies are elliptical or spiral galaxies, but thanks to the Hubble telescope, we know that going back in time, namely to further distances, galaxies were very irregular and mostly smaller than at present epoch. So the history of galaxies since the Epoch of Re-Ionization is a history of increasing structure of the galaxies. And one of the, at the end of the Epoch of Re-Ionization, we know now at redshifts greater than 5 up to redshifts of 7 and something, already 400 very massive black holes, which are a main puzzle at this time. We don't know how black holes of 10 to the 9 and up to 10 to the 10 solar masses in quasars could have been already formed in place when the universe was less than 10 to the 9 million years old. And this is one of the frontiers in the area of black hole, and also in the cosmological frontier of what is called the Epoch of Re-Ionization. So black holes with masses as large as that of M87 were already in place when the universe was about 700 million years old. And this is a big puzzle now. And the work that has been done so far indicates that probably very massive black holes were born before and grew faster than the stellar bulges. And this is something that comes from observations so far. The second issue is that from these black hole observations by all the means we had today, ALMA, Hubble, etc. The second question is whether at those times massive black holes could play a very important role in the formation of the stellar structures. And there are indications that at the very high densities of gas in the early universe, that could be the case, namely that jets from massive black holes could have induced star formation. And then another important question related to the previous talk is whether that is arising now, whether black holes could be an important component of dark matter. And this is a question that also arises from the fact that black holes so massive are found so early in the universe. Now, let me remind you some properties of black holes, and in particular, the properties of black hole jets, because we approach the unknown from what we already know. And we know that supermassive black holes are sources of high energy radiation and also of relativistic jets. And as you can see here, from a very compact region are produced jets that can go millions of light years away in a collimated way. And we know that the collimation of those jets are produced by magneto-hydrodynamic mechanisms, and those jets constitute today one of the main laboratories for high energy physics, because the energies produced in these jets are enormous, as I'm going to show. So, and we know these relativistic jets are powered by the spin of the black hole and the angular momentum of the accretion disk, and collimated by magnetic fields. Now, in the year 1992, 1994, and so on, since that epoch, we started to become to realization that the physics associated to the stellar black hole sources are essentially the same as the physics observed related to accreting and ejecting supermassive black holes. And that was thanks to the mission French Soviet Union collaboration in a satellite called ICRANet to detect high energy sources and soft gamma ray sources in the sky. And so it was found in 1992 that stellar mass black holes could produce relativistic jets that, instead of going up to millions of light years, go up to tens of light years. And then in 1994, it was found that in stellar mass black holes are found also superluminal motions, apparent superluminal motions, as in quasars, namely in supermassive black holes, jets. And so in 1994, it was observed a major ejection event from a black hole located at about 8 kiloparsecs from us, indicated here by a cross, and jets were observed during a period of about 2 months. moving at apparent speeds greater than the speed of light, and the kinetic energy of these jets produced by a stellar mass black hole of 10 solar masses is equivalent, the kinetic energy, to about 1/3 of the moon mass moving at 98% the speed of light. So the energy, even in these stellar mass black holes injected in the environment, is enormous by these jets. So we know now from observations that we call these jets microquasars, these stellar black hole jet sources, microquasars, to indicate that all the physics around these sources, these two types of sources, namely supermassive black holes observing quasars and microquasars observed in stellar mass black holes, are essentially the same, namely the equations, all the phenomenology is the same, but the scales of length and time of the phenomena are proportional to the mass of the black hole. And this is why, if we are interested in the physics of accretion and ejection in black holes, is necessary the synergy between the observations of these two classes of black holes, supermassive and stellar mass black holes. So the question that arises is, are the origin and growth mechanisms of supermassive black holes, namely black holes with more than 10⁶ solar masses, and stellar mass black holes, namely black holes of less than 100 solar masses, completely different? And the other question that arises, observing at this diagram, where are the intermediate mass black holes, namely black holes with masses in between 100 and 10⁵ solar masses? Why we do not observe them in such prolific way as we observe stellar mass black holes? So these are current questions for which we propose with my colleague Luis Felipe Rodriguez some possible answers. Now, the other fact, new fact that is becoming observationally evidence, is that relativistic jets from black holes can trigger star formation. And one case, very special case, on which there were two Nature papers by the same group of people, is the formation of stars, of clusters of stars in a dwarf galaxy that is the best analog that we know so far at a distance of 9 megaparsecs of the dwarf galaxies that would have been formed during the epoch of re-ionization. And you can see here a diagram. This is the green is the radio emission from what we believe is a massive black hole of about 1 million solar masses that is producing from its jets two regions of active star formation due to the impact of these very energetic jets that pile up the high density gas that ultimately collapses into the formation of massive stars. Observe in Pachen alpha of the recombination line of hydrogen. But here there is the absence of stellar spheroid, which suggests that in this galaxy, this small galaxy that is forming, is very rich in gas, the massive black hole of 10 to the 6 solar masses is formed before the formation of stars, and in particular stellar bulge. So black hole jets inject very large mechanical energy in the high density gas, triggering star formation, in this case at a distance of 70 parsecs. So these are observations, and very likely these things like this happened very early in the universe. So in the local universe, it is observed, here you see a diagram that is showing the black hole mass of a galaxy against the mass of the central stellar bulge. And there is a very nice correlation between these two masses. Typically, the masses of the central bulges are 1,000 times in stars than the mass of the black hole. However, very recently, observations with ALMA and other instruments have shown that for quasars at redshift greater than 6, namely when the universe had less than 700 million years, the masses of the supermassive black holes against the masses of the stellar bulge, you see here is reproduced the local correlation. The masses were about a factor of 10 times larger than the stellar bulges, and well, much more, about 100 times larger than the overall stellar mass of the galaxy. So it seems that the supermassive black hole to stellar bulge mass ratios at redshift between 6 and 7 are 10 times higher than in the local universe. So, which suggests that in the early universe, supermassive black holes come before and grow faster than galaxies. And so there is a basic difference apparently between the present and the very early epochs of the universe. So black holes seems to come first before the stellar structures. So here, well, we are now, well, people is working on how were born or grown the supermassive black holes of 10 to the 9 solar masses when the universe was less than 700 million years. And here you see a diagram published by the collaboration led by Wang, where for all black holes, there are 7 black holes with redshifts greater than 7. These are supermassive black holes of 10 to the 8, 10 to the 9, 10 to the 10 solar masses. if one assumes that these black holes, you see here is the mass of the black holes as a function of redshift. In other words, as a function of time since the Big Bang. And if one assumes that the black hole masses grow at the Eddington limit with a radiative efficiency of 10%, the seeds of these black holes should be, starting at a redshift of 30, should be at least 10 to the 3, 10 to the 4 solar masses under this assumption. So you can see that how, for instance, this supermassive black hole observed here with a mass of 10 to the 9 solar masses, more, a few times 10 to the 9, under this assumption, should have already at a redshift of 30 a mass of larger than 10 to the 10,000 solar masses. So the question that one can ask, can this growth be sustainable for 600 million years? So, because accreting black holes at the Eddington limit produce feedback. It produce jets and winds and so forth. So can be sustainable, this growth during 600 million years? Well, one possibility is that the accretion of black holes very early in the universe was not at the Eddington limit, but super Eddington. And in fact, we observe super Eddington accretion in stellar mass black holes like GRS 1915, SS 433. And the condition is that the density, the column density of gas should be enormous, should be very large. These two sources, for instance, in stellar mass black holes, where very clearly the accretion is super Eddington, are fed by stars that the first one is a red giant, and the second one is a donor star, is also transiting from the main sequence to the giant and supergiant region of stars. So these black holes are embedded in very large column densities of gas. So the growth of massive black holes, in fact, observationally and theoretically, show that depend essentially from the environmental gas density. And in fact, in the very early universe, at redshift set, the gas density should be up to 1,000 or more times the typical global gas densities as in the local universe. And in fact, studying quasars at redshifts of 6, it is found that the mass of gas of these host galaxies of very energetic quasars is of 10 to the 11 solar masses. And the column densities are 10 to the 23 per square centimeter. And most of the emitting hydrogen detected with ALMA is produced from regions that are have densities larger than 10 to the 4 atoms per centimeter cubic. So this is a very recent, very interesting paper. So the point is that for super Eddington accretion, you need very large gas densities, which are expected to have taken place very early in the universe. So the second question is, perhaps we can answer the second question, are the majority of intermediate mass black holes of transient existence? So their existence was mostly in the very early universe. And once they started to be built, these intermediate mass black holes, they will have grow without any other possibility to become supermassive black holes. And this will be why intermediate mass black holes are so dearth in the local universe. So one of the questions is that whether these progenitors of supermassive black holes of 10 to the 9 solar masses with masses of 10,000 or more solar masses could be of primordial origin or not. And well, this is a question related to the previous talk that I can speculate more in the questions. So some of these, one thing I wanted to stress is that with the James Webb Telescope, on which there is a press release today, in fact, is working perfectly, better than expected. With the James Webb Telescope, we will be able to detect and see these supermassive, these intermediate mass black holes in their way to become supermassive black holes at redshifts of up to 15, namely when the universe had 300 million years. But then earlier than this epoch, we will be able, we hope, to see how these black holes have grown using SKA, using the 21 centimeter line of atomic hydrogen. So this is something very early, I will say within 1 year, we will be able to see these intermediate mass black holes growing to become supermassive black holes, because with the James Webb will be the possibility to detect these mini quasars. And then earlier on with SKA, we will be able, by the production of absorption in the atomic hydrogen of the interstellar medium, see how these black holes grew from redshifts of 20 up to 15. So we are in an epoch where we could solve observationally all these questions on the formation of these supermassive black holes so early in the universe. So among all these black holes in quasars of the epoch of re-ionization, there are 5 that are radioluminous, and they will be very useful you can see here the radio data and the infrared spectrum of these sources, and since there are these very luminous radio quasars, it is expected that besides the cosmic microwave background may exist also a cosmic radio synchrotron background that at present is of unknown intensity. The question is that we know that if this cosmic radio background produced by this very early radio loud quasars should be impressed as an absorption signal in the 21 centimeter line of atomic hydrogen, highly redshifted, observed with SKA, and perhaps other instruments also. So there was a first tentative detection of this absorption expected by an experiment called EDGES. And here you can see this is the brightness temperature of the atomic hydrogen, highly redshifted atomic hydrogen, as a function of redshift. And the theoretical predictions are here, depending on the X-ray emission of the black hole, is for different colors. But the reported EDGES absorption was in between 2 and 3 times larger than the predicted absorption against the cosmic microwave background. So to match EDGES, there should be, according to this very well-known equation, there should be a cosmic radio synchrotron background that is about in between 1 and 2 times the cosmic microwave background, which is very large. This is the EDGES detector in Australia, in the desert, and we asked with Luis Felipe what type of sources could produce such a large cosmic radio synchrotron background, and we have analyzed that, and this is a table resulting from the observations, comparing the observations that we have for different type of sources like Cygnus X1, Cygnus X3, Sagittarius A star, 30 Dorados, Centaurus I, M87, up to 20, and we find that only very luminous supermassive black holes, like one of the radio-loud black holes at a redshift of 7, that is here, could account for a radio synchrotron background so strong. So, and from these observations, we have inferred that this black hole, this radio-loud black hole, should precede the formation of galaxies. So recently, in February 2022, another experiment called SARAS-3 in a lake in India, a very high lake, with a radiometer, they didn't confirm the edges result. The problem is that we need interferometers like SKA, because the global observations made by edges and SARA are subject to systematic errors that are difficult to control. And furthermore, the expected signal is about 3 orders of magnitude less than the galactic emission. So only interferometers will be able to detect these predicted absorption signals in atomic hydrogen. So the conclusion is that we have to wait until interferometers like SKA, the Square Kilometre Array, be already built to detect the expected H1 signals. So the conclusion is that we are right now in a very exciting time, because massive black holes and galaxies in the epoch of re-ionization may be detected directly with the James Webb Telescope up to redshift of 15. And I think that will start to happen right now, because there are programs already to try to detect these growing black holes, or indirectly up to redshift of 30 by observations of the redshifted 21 centimeter line of atomic hydrogen with interferometers like SKA. You can see here SKA in development with future low frequency or with future low frequency radio observatories on the hidden side of the moon. Perhaps the interference from Skylink and so forth is so strong that perhaps we will have to go to the hidden side of the moon. So all this, this is a very extended review published in New Astronomy Reviews. It took with us, with Luis Felipe Rodriguez, 2 years and a half to work it out, and it's a very extensive with where we tackle several problems about well, this frontier of cosmology that is the epoch of re-ionization. Okay, thank you.
Also, absolutely fascinating presentation. And many of these results are classic, but the logic in which you are developing is quite new. And the frontier that they are coming from observations are also very exciting. In our part of the contribution, we wonder about this 10 to the 3, 10 to the 5 solar mass black hole, which seeds the universe at very, very high Z. And we are currently dreaming that maybe this 10 to the 3, 10 to the 5 solar mass object are related to the same object, which is our galactic center, due to our INOS. And we are working on that. And let me thank you for this very, very beautiful presentation, and see if there are questions.
Yes, I have a question. Felix?
Yeah.
Felix,
There is an echo. I
I think now
cannot
it's
hear
okay.
very well.
Felix, thank you for this talk. So I wanted to ask you, which is the actual status of the accretion, the accretion rates needed for a standard population 3 stars in the early universe to grow fast enough in order to go to a 10 to the 9 solar, 10 to the 8, 10 to the 9 solar masses black hole in already at redshifts, let's say 7 or 8, where there have been detections in quasars of these black holes. Because I'm wondering about the beyond the Eddington accretion rates in this so short time. Can you comment, please?
Yes, starting with actually there are models this time, not assuming very massive POP3 stars, simply assuming POP3 star of 100 solar masses. Andrew Keane has, with a collaborator, developed a model where you can keep Eddington or slightly super Eddington accretion for all time. I mean, by a mode of accretion that starts isotropic, and then as it evolves through accretion by a disk of gas. And this is a model and that takes into account observations, and they can produce these supermassive black holes at redshifts of 7 or 10 to the 9, starting from black holes of 80 solar masses, for instance.
I see, Felix, but sorry. Yeah. Thank you, Felix. I want to shoot one next short question. But so, what you're telling that this model you have provided or with your colleagues is depends on the accretion physics of this hypothetical disk in the high Z universe, right? It depends strongly on this assumption, which need to be yet tested observationally, right?
Right. It depends on how evolves the geometry of the gas accretion. At the start is chaotic. Yes, and so you get then easily a black hole that accretes rapidly, and then is through a structure of disk, because the black hole starts to get some spin, and then you get a steady accretion through a disk that is formed progressively. Is the evolution of the geometry of at the beginning is chaotic, isotropic, which avoids the problem of feedback by the black hole.
Very good. Since you are in presence, I would like to ask Carlos to speak about a prize, the 2022 ICTP-SAIFR Prize in Classical Gravity and Applications, which has just been attributed to the work in ICRANet and in Argentina and in South America more generally by Edward Becerra in Colombia and Carlos Arguelles in Argentina. This is a very nice prize that we have just received, and I will ask Carlos to comment about this, and at the same time wishing very much that this will be a pre-start of opening, thanks also to your help, and of ICRANet Center in Argentina, and more generally in Latin America, including Mexico and, of course, Colombia. I ask Jorge to proceed. Carlos to proceed.
One minute, please. There are some issues.
Jorge is listening.
Yes, I'm here. May I in the meantime, maybe I want to ask something to Felix.
Yes, absolutely.
Related to his presentation. I don't know if Felix is listening or not.
Yes, I'm here. Yes.
Okay, yes. Because
go ahead.
It was very nice that that plot showing the going back in time to the seed. So, but a question about that. That plot assumes that the black holes are accreting at the Eddington limit, right? So there is a degeneracy between the mass of the black hole, the seed black hole, and the efficiency of the accretion process, right? So I suppose that you will get higher mass for the seed for a relatively inefficient process, right? So there is if that those observations that will come, there is a way to break that degeneracy.
What do you mean by?
I mean, if I see some object that is luminous, okay, it has some luminosity. How this luminosity can be produced by a lower mass black hole,
right,
with a higher efficiency, or with a higher mass black hole with a lower efficiency.
Yes. Yes. Well, the assumption of these diagrams is essentially that the accretion is continuously at the Eddington limit with a radiative efficiency of 10%, as observed, usually in the local universe. And then you evolve continuously. So, as you say, very likely there are periods where this is not the case. I mean, what Wang and collaborators have done is simply take the most simple assumption and see what what mass seeds for the black holes at a redshift of 30 could be obtained. So we know the process of accretion in black holes, especially from stellar mass black holes, which allowed us to study in terms of time with a very high resolution, that they vary very much. I mean, they can go in certain periods of minutes up to 10 times Eddington, and then go down the accretion rate. So this is something they have calculated on the very simple assumptions. the observations are going to show, this is what I want to stress, is that the observations will show how all this goes up to a redshift of 7 with the observations by the Webb telescope and later, I hope, with SKA. The first thing will be the James Webb. I mean, they will be able to detect black holes with much less masses, namely that produce the same phenomenology as the most luminous quasars, but with masses of, instead of 10 to the 9, 10 to the 7, 10 to the 6, 10 to the 5, 10 to the 4. This is our expectation.
Very good.
I have a question to the previous speaker. I'm surprised that the maximum mass of black holes found in the local universe that have, for instance, M87, 10 to the 9, up to 10 to the 10, are found at those very early epochs. So my question is, I didn't get very well the reason why the black hole masses that will constitute some fraction of dark matter could not be very massive. I didn't get very well. Because if that is the case, if this growth doesn't take place, then the supermassive black hole could be primordial.
Stefano, I think it was a question for you about why primordial black holes will have a mass as large as 10 to the 9 as we see in M87, but I think I think you show that 10 to the 9 solar masses are ruled out already as primordial black holes, right? As the main candidate of dark matter.
I think, sorry, I think that was the black holes with masses greater than 10 to the 15 grams.
So this. The 10 to the 15 grams was the lower threshold, below which you would not have any primordial black holes at all today because they would have already upgraded. So these are very small black holes, like small asteroids, 10 to 15 grams. And the question that you posed me about 10 to the 9 solar masses, yes, 10 to the 9 does not fall in any window where you could make 100% of dark matter. It was fairly constrained. I can retrieve that plot and tell you exactly by how much, but the windows where you could make 100% of the dark matter in the high mass range was higher than 10 to 14 solar masses. So definitely 10 to the 9 was fairly constrained. I'm opening my presentation right now to just check if you want, but yes, I can see that. So 10 to the 9 solar masses, you can make at best a fraction in dark matter of 10 to the minus 3, 10 to the minus 4, so 1,000th of the dark matter. So I don't know if this was the question that was asked.
can you show the diagram where you had before going to the one solar mass?
I cannot hear him.
Oh, sorry. I think now here. Felix, I don't know if he answered your question.
Well, we can talk later. Yeah, Remo stopped me when I was going to ask you this question. That would have been very timely. Yeah. And I had another question: is whether the experiments macho because I believe there could be primordial black holes, and I'm very interested in this possibility. But for instance, the macho experiment and Eros experiment constrain the possibility of primordial black holes in the halo of our galaxy, and if that is the case, what is the constraint?
Can I answer?
Yeah.
Yes, in fact, the machos are part of that constraint plot that I showed, and the many acronyms and small that were reported there refer to all different classes of experiments that have been done and observations, and only one of them was actually machos. And if I remember correctly, they would constrain in their relevant mass range a fairly big chunk of fraction of dark matter that you can make in primordial black holes just thanks to machos. So yes, they do very much enter the picture, and they are, of course, well taken into account. And Carr has done a very beautiful job in putting out these reviews where he goes very fine details about every single different observational constraint, and of course how much these constraints quantify the fraction that you can make in primordial black holes, and it goes, of course, very much in details about machos as well. So yes,
Okay.
I don't know if this answered the question.
Okay. Okay. Thank you. Yeah, I know the review by Carl, the recent review. Yes, I had to go back to it. Yeah. Thank you very much.
We will have next week some presentation from Pescara about some important understanding of how GRB behave at IZ, and how the observation of a GRB is a very, very strong function of the cosmological redshift. We will have this presentation by Yang Li and the author, and I urge you, Felix, to come back to this presentation next week, because there are a lot of news.
Okay.
And it's very exciting, very important. In the meantime, as I promised before we break, I ask Carlos to speak about this award to Edward Becerra and to all the group, and wishing for development in Latin America of ICRANet. All my best. Carlos, please.
Okay, so thank you. Let me see how minimize this. Yes. So okay. Yes. Take this out. Yes. I will talk, unfortunately, Edward Becerra couldn't be here today. This is to present a few slides of the recently ICTP, so the American Institute for Fundamental Research Prize. This, as you probably know, ICTP in South America works in collaboration with ICTP Trieste, FAPES, and IFT of Sao Paulo. And every year, since a couple of decades, they recognize recognize PhD thesis research of outstanding quality and achievement in classical general relativity and applications. And this year, there were 3 prizes, 1 main prize and 2 honorable mentions, one of which was awarded by the PhD thesis of Edward Becerra Vergara, which is one of our collaborators, and the works mainly awarded are related with this. You can see here in the upper panel of the slide, the astronomy and astrophysics papers in 2020, and the Monthly Notice work of 2021, and the last paper, Monthly Notice letter of 2022. So I will present the outline of research in this talk. Tomorrow I will give a full review of the research program of what you can do with fermions and gravity. But today I will only talk about these 3 papers, these 3 results about the dark matter in our galaxy, in the Milky Way, and the galaxy center. So let's move fast to the talk. So the challenge, let me first give a brief introduction. So the challenge is if you assume that we have a fundamental particle, let's say a fermion, which is there after inflationary epoch and decoupled from primordial plasma in a certain regime, then the challenge is to study how the first linear evolution perturbation, intensity perturbation, and then its corresponding non-linear evolution can go into dark matter halos made out of these fermions, and which are the morphological consequences of these fermion on galaxy scales. So I don't need to present the motivation of cold dark matter, which was given in the previous slides, but one of our speakers, and also large-scale structure and rotation curves. But so let's start talking about the several different terms that dark matter in the galaxies already, all the way to galaxy down from the primordial decoupling all the way down to galaxies. Yes. So as you know, dark matter is a collisionless. We can deal dark matter as a collisionless fluid. So where we would like to study the relaxation of this collisionless dark matter. And one way of doing that, if you see the equation of the left, we have the so-called Blasov-Poisson equation, which is the equation which is typically used in embodied simulation to study the evolution of the phase density at trickle level. Of course, in by simulation, you don't study the evolution in this due to this differential equation, but numerically. But in this case, is it possible to study this evolution of the phase density analytically, and interestingly by making expansion in the phase density into a coarse-grained term f bar plus a fluctuation, and replacing this in the original Blasov-Poisson equation, you can have another equation that you can see on the right, equation 1, which is for the evolution of this coarse-grained phase density, which is which takes the form of a convection diffusion equation. With in the right-hand side, you put all the fluctuations averaged. So, so the challenge is if it is possible to analytically have a most likely coarse-grained phase density at relaxation out of this kind of kinetic equation with gravity. So this was solved by, this can be solved by a maximum entropy production principle, that you assume that the coarse grain entropy is maximized, and you can find that the most likely coarse grain phase space density is of the Fermi-Dirac type, as you can recognize by the in the denominator with this 1 plus e to the inverse of temperature times energy plus alpha, and in the numerator you have a term which accounts for the escape energy condition. So for energies above this escape energy E sub m, which is the in this formula here. So you do not have more particles in your system, and therefore your system is self-bounded. This solution is a generalization of the original work of Lindenberg about biological relaxation, but was formalized and improved by Chavanny in the works of 1998 and 2006. And interestingly, one can assume that the elementary blocks are fermions, and therefore, in that case, the maximum accessible value of the distribution function is fixed by the Pauli principle. Therefore, this eta 0, which is the maximum accessible value, and now takes this traditional form proportional to the fermion mass to the fourth divided by h cubed. Therefore, once we have this most likely coarse grain phase space density at relaxation, we can wonder how can we build these dark matter density profiles. And the first key concept is that fermions under cell gravity do admit a perfect fluid approximation. This was solved in the late 60s, and therefore it allows us to use Tolman-Oppenheimer-Volkoff solution in spherical symmetry for this system of cell gravitating fermions at finite temperature. And therefore, we can build the so-called equation of the state out of this density, as you can see here, in pressure, in terms of this coarse grain phase space density F of Fermi-Dirac type that I've shown before. At this level, we will deal with the energy fully relativistic, but that does not mean that the particles are relativistic, but depending on which regime are in the galaxy, you can be from relativistic to non-relativistic. So this is a very general case. And this is, as you can see, this equation of state is 4 free parameters: the particle mass, the temperature, which is called beta as dimensionless magnitude, the theta parameter, and the W, which is the cutoff energy parameter. So with this, you write down the Einstein equations for this perfect for this fluid system, which you recognize the TOV equation for the spatial temporal metric function, then the Klein and Tolman equation of zero and first law of thermodynamics and relativity, and the energy conservation along geodesy. So you have to solve this system, which is a system of a couple highly nonlinear ordinary differential equation system, when you can see that is sourced by these pressure and density terms that you can see on the left. This hat is because it's in the equation on the right, is because are dimensionless equation. And this is therefore a boundary condition problem that you have to solve for regular condition at the center. So our mass is not singular, it is regular at the center. And we have the 3 parameters of the degeneracy of these fermions, the temperature, and the cutoff energy. So the most general solution you can find out of this equation has this format you can see here on the plot, in which interestingly you can see the both regimes are included in this solution, meaning starting from the outer region where the fermions are thermal pressure supported, and going towards the center, fermions become degeneracy pressure dominated due to Pauli principle. This implies that the density profile can develop an interesting plateau tail, a plateau and then a tail, similar to NFW or INAFW profiles on halo scale, where observables can be achieved. And then towards the center, it develops a dense concentration of dark matter which can be very compact, as you will see in a moment, and these solutions depends on the particle mass. This picture shows an example of a typical spiral galaxy where the boundary condition fixed has been fixed as a 10 to 11 solar masses with a radius of 10 to the 4 parsec in the halo, here fixed. And it can be shown that for the generacies larger than 10, central generacies of fermion, the central core is really a so-called quantum core, because the thermal de Broglie wavelengths of the particles there are larger than the interparticle mean distance. Therefore, this condition is satisfied. And then the challenge is now, which was the main works of Edward Becerra that led to this prize, is if we want to apply this profile to our galaxy, which is the role of this central core? Can this central core mimic the dynamical effect of the central black hole hypothesis? Well, so let me just go to next slides. More details will be presented tomorrow in the longer review. So if we move to galactic scales, so the rotation curve of the Milky Way, as I was saying, we have the Milky Way is governed by, let's say, 4 main components. The central parsec, governed by this dark compact object of presumably a black hole of 4 million solar masses, the central bulge, the flat disk, and the outer halo. So these 4 components, where you see the flat rotation curve on linear scale, typically here on the picture of down right. And in the picture of down left, you see a logarithmic plot of the so-called grand rotation curve of SOFUE, data of SOFUE 2013, and then updated in 2017 and 19, where it's possible to link the innermost parsec of the galaxy to the outer halo. Of course, the rotation curve of the Milky Way is due to the disk and from this to outer halo scales, and the inner part, as you know, has a has a non-circular motion, has a bar and some complicated dynamics, but SOFUE was able to disentangle or separate the effect of the radial motion of the particle there with the tangential components. And therefore, the error bars you see here, the large error bars you see here, are accounting for these non-circular motions. So this is, you can think of an effective rotation curve going from first parsecs to all the way. So any model of dark matter that would like to be applied to Milky Way should be able to be at least within the error bars of this data. But we can go even further inside, for example, by considering the S cluster stars, which now goes down to milliparsec scales, that also were introduced in the talk before, where the S stars, one of the main candidates is the S2 star, whose pericenter achieves order 610 to the -4, so it's already in milliparsec scales, and is the best dynamical tracer of the central gravitational potential, leading to a constraint in the central mass of about 4 million solar masses. Therefore, these papers I was talking about our model applied to Milky Way were based on this question: if the overall gravitational potential of these core halo dark matter profiles can explain the Milky Way rotation curve as well as the S-star dynamics without the black hole hypothesis. So a hint to answer this question is, of course, you have to solve this boundary condition problem that I've shown before, of the equation of these gravitating fermions with specific boundary conditions, meaning in this case, we have solved, it can be done in different ways, but the most, let's say, basic way is to fix 3 observables, one per each free parameter, which is the mass in the outer region, which is constrained at 40 kiloparsec by the Sagittarius dwarf satellite galaxy, another mass of 10 to order 9, 10 to 10 solar masses at 20 kiloparsec, typical scale on halo scales. And of course, the central core, we want to be fixed with a mass of 4 million solar masses. So interestingly, the answer is yes, there exists a family of solutions of dark matter distribution, which, as you see in the picture of the right, can not only reproduce the rotation curve of the galaxy. You see here in red the baryon distribution of bulge and disk, and also on top of our solution for dark matter, but also it increases towards the center due to this degeneracy of the dark matter, which can account for the average circular velocity of the 8 best resolved S stars, as you can see here, labeled by this blue process, blue little stars. The solution, the gray dash solution, corresponds to a particle mass of 40, in this case, of 48 kilo electron volt, and the compacity of the compactness of this core is around 1,000 Schwarzschild radii, a bit just marginally inside the pericenter of the S2 star, while the solution of continuous black corresponds to a particle mass of 345 kilo electron volts, which corresponds to the most compact core in these dark matter configurations, above which you will collapse to a black hole. As you know, every solution of gravitating fermions in general relativity have a critical mass of collapse, and in this case of these fermions correspond to this mass. Interestingly, another consequence of these profiles is that, for example, if you wonder what about going to smaller particle masses, for example, below 1 kilo electron volt, as you see here in the plot of the dot orange, the core will be too extended in such a way that we overshoot the inner rotation curve of the galaxy. And therefore, this is an independent constraint of the particle mass of the dark matters, independently from cosmology. As you know, the so-called Gannon-Surmain limit or phase-space bounds that sometimes I refer, it poses lower bound on the mass of the dark matter particle in the above a few kilo electron volts, and this is in agreement with those constraints. Well, this result, this is a bit of the our rotation curve, which I will speak more in detail tomorrow. But let me go faster. There is some delay in the internet. Sorry. Let me go faster. Yes, to one of the main papers that were awarded by this in this PhD thesis of Edward, and correspond to our first test to this to this scenario of fermionic dark matter core by analyzing in detail the data of S2 and G2. So in this case, because former slide I showed the average circular velocity of stars, yes, and now I will show the geodesic motion, which is without this hypothesis, the geodesic motion. So we take the data of the BLT, Keck-1-2, and Gemini North and Subaru, and a challenge is that this model should be able to explain the multi-year accurate astrometric data of S2, including the relativistic redshift that was detected a few years ago by the gravity collaboration, and well, as well the G2 star. So I will just mention now in this talk the main result, which is that a core of dark matter, of this degenerate dark matter core of roughly 4 million solar masses, can explain the geodesic of this two star. You can see here in the picture of the left all the astrometry in right ascension and declination, with similar accuracy than the black hole scenario. As you see here, the reduced chi-square, the average reduced chi-square of all the data in the black hole and our model are very similar. and you can see here as well the residuals, which are all around similar values. Just to finish this, interestingly enough, also you can check for the radial velocity, so, and compare the redshift excess. What you see here in the picture on the right, this red curve with this peak shows the excess of redshift due to a general relativistic effect in the redshift of the function when compared to Newtonian. So if the dashed line 0 corresponds to a purely Newtonian case, and you see here that the data are clearly showing that it should be an excess due to redshift excess in the motion of this star, which is also predicted by our model. And then finally, we have also analyzed the precession of these two stars, but this will be a talk for tomorrow, in the afternoon of tomorrow. And I will leave you just then with the last slide of today. Sorry, it's a bit, yes, which is this slide where we have in the last work of Edward by ending his PhD about the 17 best resolved S stars, which altogether which can be as well reproduced by our model with similar accuracy than the black hole. Thank you very much.
Thank you very much, Carlos. If there are questions. And otherwise, let us thank all the participants of this very interesting session, starting from Stefano Bondani and Federico Re, Felix, Carlos, and also a very welcome participation from org. Therefore, let's conclude, and we will have a small ceremony upstairs shortly. Thank you so much, and let's go back to the main program tomorrow morning, still from Nice, starting at 9 o'clock. Okay, therefore, we are concluding this morning session after the presentation of Federico Re, Stefano Bondani, and beautiful presentation of everyone, but especially of Felix MIRABEL, and then the celebration of the 2022 ICTP-SAIFR Prize to Edward Becerra and all our team. Well, let's see if Felix has any comment. Otherwise, let's thank everybody again and conclude. See you tomorrow again from Nice, starting at 9 o'clock. There are a few changes in the program that we will announce. Thanks.